Hello. Today we discuss the classical definition of circular functions or trigonometric functions, sine and cos. So using the power series E of x, so we start defining a function c of x first. Okay, so this c of x is defined as half times e of ix plus e of minus ix. This I is our complex number. So using this I, we define c of x, and this is a real function. In fact, this is a complex number and this is its conjugate. So sum of complex number and its conjugate will give the real part, or 2 times the real part. So we will get the right hand side as a real number. Similarly, we defined another function s of x, that is 1 by 2i times e of ix minus e of minus ix. So this is again a real function. Okay, so this is defined as c of x and s of x. Now we know that e of z conjugate is same as e of z whole conjugate. The whole conjugate. This is because e of z is a power series, so 1 plus z plus z square by 2 factorial plus etc. This is e of z. Then e of z conjugate will be a conjugate of all this. Okay, so we can take the conjugate outside. So we have e of z whole conjugate. So we have this result. Now we write what is e of x. E of ix equal to, from this we can write this as c of x plus I times s of x. Okay, when you multiply this with I and add these two functions, then you will get e of ix is equal to c of x plus I s of x. So this is the connection between e of ix and c and s in the reverse order. Now we can say that this c of x and s of x are the real and imaginary parts of this function e of ix respectively. Okay, then what is mod e of ix whole square? Mod e of x whole square will be e of ix into its e of ix conjugate. So we know that e of ix conjugate is e of minus ix. So this is e of ix into e of minus ix, that is equal to e of ix minus ix, because e of z plus w is equal to e of z into e of w. So using that fact, this is e of 0 and that will be 1. That means the modulus square of this is equal to 1. So from this equation you can say that c square plus s square is equal to 1, because that is the square, the square of the modulus of this e of ix. Okay, now we have e for e of ix, mod e of ix equal to 1 for all x belongs to real numbers. Okay, for all x, for our real number x. Now we have what is c of 0. C of 0 by definition, this is e of 0 plus e of 0, that is 2 times e of 0, that is 2 divided by 2, that is 1. And similarly s of 0 is e of 0 minus e of 0, that is 0 itself. So we have s of 0 equal to 0. And we have what is c dash x, that is the derivative of this. When you differentiate this, the first we have I times e of ix, and this will be minus I times e of ix. Then you can take that I out, and by rationalizing you can get that is, first of all we write I times I by 2 times e of ix minus e of minus ix. Okay, so we can write it as minus 1 by 2i e of ix minus e of minus ix. This is nothing but our minus s of x. So c dash x equal to minus s of x. Similarly, you can evaluate s dash x, then you will get what is same as c of x. Okay, now we observe the monotonicity of these functions. We write that exist. First of all, we know that this c of x equal to c of 0 equal to 0, c of 0 is equal to 1, and we assert that there exists a positive integer x such that c of x equal to 0. That means from this equation we can say that s has a 0, okay, s of 0 equal to 0, and we will assert that this c has also a 0, okay. That is because if it is not true, then c of 0 equal to 1, that means for the contrary, if it is not true, we have c of this quantity is 1, it follows that c of x is always greater than 0. Okay, we know that the c is a continuous function, then we already know that c of 0 is equal to 1 here. If there exists any value at which the c is negative, then in between those two values we can get a 0. So if there is no 0, then the c of x is always positive. Okay, so if c of x is always positive means for all x greater than 0, if x greater than 0, we have c of x is greater than 0. If it is not true means there is no positive 0 for this c. Okay, so that is our assumption. So in that case we can get this c of x is nothing but s dash x. Okay, so s dash x is greater than 0 for x greater than 0. Okay, so what is the meaning of this? Derivative is greater than 0. So that means s of x is increasing. Okay, s dash x is 0 means s of x is increasing. So we know that 0 less than s of 0, and for that we write, from this you can write s of x is increasing. We know that s of since this positive quantities, for these positive quantities, if we take 0 less than x less than 0 less than x, we can get s of 0 is less than s of x due to the monotonicity. So that implies 0 less than s of x. Okay, that means for all x greater than 0 we have s of x is always positive. Okay, now we have 0 less than x less than y. We have, if we choose any two numbers x and y such that x is less than y, we have s of x into y minus x can be written as, or we can write this is less than integral x to y s of t dt. Okay, this is because this quantity is, we know that s of x is increasing function. So from among these values, if we choose any t in between x and y, s of x is always less than s of t. Okay, so this is the fact. Then we have s of x into integral integral x to t x to y 1 dt is always less than integral x to y s of t dt. Okay, because of this fact we can get this one. Then this is nothing but the left hand side of this inequality, s of x into y minus x. So that is always less than integral x to y s of t dt. But we know that s of t is nothing but integral x to y. S of t is the derivative of minus c dash x. Okay, c dash t. We know that c dash t is equal to minus s of t, so we can replace this by minus c dash t. So we have, this is in fact this is equal to, so we write equality here, this is not less than, that is equal to, and we can integrate this, that is minus or you write this is same as integral y to x c dash t dt. Okay, so this will be c of x minus c of y, but we know that this is always less than or equal to 2. because of this fact. This c square plus s square is equal to 1, then this modulus of since this modulus of c I of x is always equal to 1, then these two values, modulus of c of x, modulus of c of x is always less than or equal to 1, modulus of s of x is also less than or equal to 1, and that is because c square plus s square is equal to 1 always. Now we can say that this square is always less than or equal to 1, and then c of x is always less than or equal to 1. So using that fact, using the triangle inequality as well, we can get this, the maximum value of these two quantities, the difference of these two quantities is always less than or equal to 2. So what is the inference here? S of x, if you choose any x and y independent of the choices of x and y, such that x is less than y implies s of x less than s of x times y minus x less than or equal to 2. Okay, so which is a contradiction, because as this y tends to infinity, by fixing x you can get this quantity tends to infinity as y tends to infinity, so that will be a contradiction. Okay, that cannot be made less than 2. Okay, this shows that our assertion is true. So there exists a positive, this is not integer, positive number x such that c of x equal to 0. So this starts from 1, and we can get at least one real number such that c of x equals 0. So this is this one, c of x, the graph of c of x is like this. Okay, so first of all we take that as x naught. Let x naught be the smallest positive integer, sorry, positive number this is a real number in fact, such that c of x naught equal to 0. So this is the smallest such one. Okay, since the set of zeros of continuous function is closed, we can say that and c of 0 there exist such this exists because the zeros of the set of all, if we consider a set of all x such that c of x equal to 0, it's a subset of r plus, we consider positive values, then you take the smallest one. So the smallest such one exists because this is a bounded set. This starts from 0, and every bounded below set has a minimum value or greatest lower bound. And if you consider that infimum as if you consider infimum of the set, so this if this is x naught, then we know that the c of x naught is also 0 because c is continuous. Okay, so infimum exists and c of x naught equals 0, so you can easily get this number. Let x naught be the smallest such number, smallest positive number, real number such that c of x naught is equal to 0. We can easily get that number, and we know that c of 0 not equal to 0, so that's why we call this set as bounded below. Okay, so we have we define the number pi, we define this number as 2 times x naught. Okay, that means c of x naught equal to 0 implies c of pi by 2 is equal to 0. So this is the definition of pi. There are so many definitions for the real number pi, so this is one way of defining this pi. So using this power series you can define the pi in this manner. Okay, now we have c of pi by 2 equals 0, and s of pi by 2, we know that c of pi by 2 whole square plus s of pi by 2 whole square is equal to 1. So that implies c of pi by 2 is equal to 0. That means s of pi by 2 whole square is equal to 1. That implies s of pi by 2 will be plus or minus 1. Okay, but we know that this c of x is always greater than 0 in this 0 and x naught, because x naught is the smallest positive number such that c of x equals 0. So if we consider this open interval, then c of x is always 0, but this x naught is nothing but our pi by 2. So we can say that s dash x, c of x is nothing but the derivative of this. So this is greater than 0 in the open interval 0 pi by 2. Okay, this shows that in this interval s is increasing. Okay, so s of 0 is equal to 0 and s is increasing in this interval, so s cannot be negative if we consider s of pi by 2. So this implies s of pi by 2 is 1. Okay, so this proves s of pi by 2 is equal to 1. So using these two values, c of pi by 2 and s of pi by 2, then you can write e of I pi by 2. Okay, e of I pi by 2 is c of pi by 2 plus I times s of pi by 2. So c of pi by 2 is 0 plus I times s of pi by 2 is 1, then this number is I itself. Okay, now you can use the property of the function capital E such that e of pi I. What is e of I pi or pi I? So that will be e of I pi by 2 plus e of I pi by 2, sorry, multiple by e of I pi by 2, because the product of this e of z and e of w is e of z plus w. So this number is I times I, that is equal to minus 1. So e of I pi is nothing but minus 1. Okay, now what is e of I 2 pi I? 2 pi I. So this can be written as e of I pi into e of I pi. That is minus 1 into minus 1, that is equal to 1. So e of I 2 pi is equal to minus 1, sorry, equal to 1. Therefore e of z plus 2 pi I. Okay, this is always e of z into e of I 2 pi, that is equal to 1. Therefore this is same as e of z. Okay, which shows that e is a function with period 2 pi I. Okay, so this is a periodic function. So from this you can say that e capital E is also a periodic function with period 2 pi I for every complex number z. In the next class we will discuss some other properties of the C and S, and consequently we can get this C and S are the same property of our circular function sine and cos if we represent the C and S on using some geometrical figure such as triangle. So in the next class we can complete this the discussion of trigonometric functions. Thank you.